we have a tendency to perceive our experience as integrated wholes. So, things like if you flash lights while you're listening to music, you'll get this experience that the lights are actually somehow synchronized with the music, even if they're just random. The music sort of, it makes it feel like the lights are doing something sensible because you sort of try to establish some coherence between them.
I'm Ran Dror, and this is Remake, a podcast about design, systems, and society. In each episode, I talk to someone who's trying to change our lives for the better in some meaningful way, whether through a new product, new venture, or a new way of looking at the world. And I try to understand how they came to it, what makes them tick, and what we can learn from them. Today I'm talking to Professor Jay McClelland. Jay is a computational cognitive neuroscience and one of the founding fathers of the field of neural networks and deep learning in the 1980s, which led directly to today's explosion in AI and machine learning algorithms that is transforming our lives. He is the Lucie Stern Professor at Stanford University, where he was formerly the chair of the psychology department, and is currently a consulting research scientist at DeepMind, perhaps the leader in machine learning technologies today. Jay is best known for his work on statistical learning and parallel distributed processing, applying connectionist models or neural networks to explain cognitive phenomena such as spoken word recognition and visual word recognition. Today, he works on integrating language, memory, and visuospatial cognition in an integrated understanding system to capture human intelligence and enhance artificial intelligence, exploring how education into human-invented tools of thought can enhance human and machine intelligence. We spoke at the end of May 2022, and I was excited to talk to Jay because he's truly one of the founding fathers and towering figures in the field of artificial neural networks and the whole connectionist model of intelligence. Back in the 80s, this model was gaining favor largely because of Jay's work with David Rumelhart, which made so much sense and was able to prove the ability of artificial neural networks to do non-trivial cognitive tasks. I've been very engaged with the ways AI is transforming our lives, and I've written my MA thesis on AI safety and facilitated sprints on AI strategy and ethics with Cambridge's Center for the Study of Existential Risk and Oxford's Future of Humanity Institute. But what I find is that most lay people don't understand the degree to which AI algorithms are mimicking the basic structure of the brain. Whenever someone says, machines will never be able to do X, or Y will always depend on humans, I know that they're not really getting the amount of overlap between researchers studying how the human brain works and engineers building artificial versions of these same systems. In short, if humans can do it, there's a really good chance that sometime in the next couple of decades, machines will start doing it better. I thought Jay was very interesting and clear in his description of how his work came about and how his interest in cognitive psychology led him down a path of simulation of neural networks, which directly led to AI today. We covered lessons from his youth, where he moved around a lot as a child around the world and interacted with different religions and backgrounds, which helped him understand that we are shaped by our contexts and our experiences. We talk about his entry into cognitive psychology and going beyond the laws of behavior into why do people behave the way they do, building neural networks to model cognition. And, it's an interesting journey because he comes at it from a human psychology perspective and cognitive psychology perspective, and then models these things in neural networks that then become software simulations. And so understanding that these are not two different topics. These are actually the same topic, neural networks in humans and in machines. We talk about his world-changing PDP paper, or Parallel Distributed Processing, Explorations in the Microstructure of Cognition, a paper that was published in 1986 and really transformed this whole field and directly led to more and more people embracing the connectionist model and neural networks. And, the rest is history, as they say. We talk about the fact and meaning of bi-directionality in neural networks. What does that mean that information can flow both ways in the same network structure? We talk about generative models, and in this context, OpenAI's DALL-E 2 algorithm, which can create amazing illustrations and artworks. And should we credit generative or creative algorithms with artistry and give them credit for their art? We also cover the topic of consciousness. Does it extend beyond humans? Is it something that we might one day be able to find in algorithms, or maybe even today can already find in the more sophisticated algorithms? Talking to Jay really reminded me of the best in mankind. That through curiosity, asking interesting questions, and constructing thought models and experiments, we can unlock such a subtle and fundamental thing like cognition and the connectionist model, which then unlocks all of this power for society at large. We now have this responsibility to rein in the worst of mankind in how we exploit, curate, and share in the benefits of this incredible power. This will be a running topic for us, AI in the future. We explore the power of design and human-centered thinking to create a better future for everyone. This conversation with Jay is one of so many weekly conversations we already have lined up for you. This week I'm doing 3 interviews with leading authors, thinkers, designers, makers, scientists, and social entrepreneurs who are working to change our world for the better. So follow this podcast on your favorite podcast app, or head over to remakepod.org to subscribe. And now, let's jump right in with Jay McClelland. All right, I'm sitting here with Jay McClelland. Jay, welcome to the show.
Thanks, Aaron.
And so usually we start the conversation these days with kind of a COVID and world check-in, because we went through a pandemic and there's war and all sorts of things happening in the world. So I like to start with this question that people already kind of got used to is, what's it like to be you these days in the world today?
Well, I feel like I'm kind of blessed because I live in Palo Alto, California. My wife and I are old enough to have grandchildren who all live with our daughters. So we have our house to ourselves. We each have a home office where we can connect with people all over the world over video calls. And, at the start of the pandemic, I found myself feeling very isolated. And I wrote new lyrics to Bob Dylan's Stuck Inside a Mobile with the Memphis Blues Again, called Stuck Inside My Zoom Room with the COVID Blues Again. But I feel like the world has been through the COVID blues and they've been stuck inside of all kinds of things. But it's been less harrowing for me as an individual than it has been for a lot of other people.
Yeah, it's definitely been unequally distributed, the misery, and some of it is based on geography, some of it is based on job and economics, and then I find that some of it is also based on just self-sufficiency versus people who were very social and suffered more. And I tend to be more self-sufficient, and I was reading books and listening to music and living quite fine. Yeah. So we like to start the exploration together by getting to know the person a little bit. And so there's one question that I started asking, which is, what's something you've learned in childhood or early in life that still guides or drives you today, that's still with you today?
I guess I would say the most important thing is everybody sees the world from the perspective of their own experience and context. I say that because my father was a Foreign Service officer, and before I was 8 years old, I'd lived in 1, 2, 3, 4, 5 different places, and before I turned 13, I'd lived in 3 more after that. And it was in the context of that, I began to see how people in different parts of the world, approached the world from completely different sort of starting places. I think about who I am and who each of us is in terms of the context that we grew up in and was established around us by, our parents, our other significant people in our early lives, our schools, the cultures, the religions, the teachers that we had. So my own sort of primary interest as a scientist is actually to understand how experience shapes who we are.
And you told me you, at the age of 12, stayed at the Swiss boarding school, and that was also a kind of an experience of meeting other belief systems and other points of view.
Well, absolutely. So I was in Saudi Arabia for 2 years before I went to Switzerland. And I went to an American school in Saudi Arabia, but I was in a foreign country, and we would drive and visit various places, and we would see women completely covered in black veils. We would recognize that they had a completely different religion. We would hear something about their religious philosophy. But I think what struck me the most was that there was this concept that, I was a Christian and they were Muslim. But when I went to Sunday school in Saudi Arabia, the stories were just a little bit different from the ones they were more of a fundamentalist Protestant, and I had been a bit more exposed to the Anglican Episcopal sort of tradition. And these stories weren't completely the same, and the philosophies were a little bit different. I got to Switzerland and I had the same experience again. They had two choices. We could go to the Catholic or the Protestant. And the Protestant guy was a hellfire and brimstone guy. He really was a born-again Christian. And this was so different from my own experience that I was struck by it. And as a school, it came to their attention and they said, we got to do something different for these kids because this isn't what they're used to. So they brought an Anglican minister from Zurich to come and talk to us. So there's all these different religious traditions out there. And I'm like, well, okay, now which one should I think is the right one, right?
And so looking at all of these perspectives and all of these religions that are subtly different and, you're starting to kind of have questions, do you think that had anything to do with your fascination with the mind and what resulted from that? Do you think that started you down that path, or is that just a coincidence?
Well, that's a great question. And I guess I'm one of those people who doesn't necessarily think I know the answers to all of those questions. It wasn't until considerably later that I started thinking about how the mind works. That was 2 or 3 years later. Toward the end of high school, I started to think about those kinds of things. But, when I was in college, I was confronted by a situation there that was a little bit similar in that I was an undergraduate at Columbia in New York City, Columbia College. That was in 1968. And that year, we were in the depths of the Vietnam War. There was a huge set of issues surrounding African Americans and the role of the university in the community in relation to African Americans. And so actually Columbia was building a gym in a park that was considered to be a community park. And it was, just at the edge of Harlem. And so there was this big demonstration. It wasn't called Black Lives Matter back then, right? But the civil rights movement, right, with Martin Luther King and the anti-war movement kind of coalesced around this demonstration at this gym site. And then it turned out the guy who was supposed to have been my roommate that year got arrested at the gym site. And in protest of him and one other guy having been arrested, these people went and they occupied a building on campus. And I'm suddenly thrust into this situation where I'm confronted with okay, well, whose side am I on and which side is right? And why should I believe one perspective or another about exactly how to think about this situation? There were people who felt extremely strongly that the university was inherently evil and a part of the military-industrial complex. And there were people who felt equally strongly that, there were things going on in the world that the United States had to participate in, and the threat of world communism was such that we had to be fighting this war in Vietnam and all this kind of thing. And I was very uncertain, and I found myself asking the question, why are people so convinced that they're right about this when they are? And I just felt the world was so full of ambiguity. I just had questions. I didn't have any answers. But my questions were about people, why they were behaving the way they were, and why they had the attitudes and beliefs they had. I also had taken Psych 1, and I had learned in Psych 1 that people behave in ways that they regret later when they're swept up in a crowd. So this is sort of lynchings, for example. Many people in the South who had been swept up in lynching events in the South, this is what we had learned in Psych 1, would regret later that they had been swept into this and had participated in something that they found themselves to be morally reprehensible. And I was in this building listening, because I went into the building that people had occupied in solidarity with my roommate. And that's where I felt like I really started to ask questions about human nature and why people had the attitudes that they do. And, I don't feel like I have all the answers, and I don't think it's necessarily all experience. I think we have some biological differences that shape who we are to a degree as well. But I kind of emphasize the experience side.
Yeah. And so you went to Columbia, right? And then you went to UPenn for your PhD in psychology, and then getting into cognitive psychology. So tell me about that path to getting interested. When did you get interested in cognition, and how did you find yourself focusing on that?
So as an undergraduate, my experience in the field of psychology, it did include a little bit of exposure to like crowd psychology and things like that, but it was mostly focused around the idea that there was a science of behavior. There was this notion that people behave in the way they do because of their contingencies of reinforcement that they have experienced. This was the Skinnerian vision of behavior. And the other part of the Skinnerian vision of behavior was that it wasn't scientifically valid to ask questions about thoughts and what's going on between the stimulus and the response. The only things you could observe were the stimuli and the responses. So don't make up stories about the stuff that goes on in between. That's just, you're lost in some cloud cuckoo land of fantasy. So just stick to the laws of behavior. And I found the laws of behavior compelling because you could definitely get a pigeon to do very, very different things depending on the contingencies of reinforcement. But I also found myself trying to figure out why the pigeon was doing that. What were the mechanisms that were giving rise to that, right? So, yeah, I didn't know how to think about those mechanisms at first. But I will say that I also took a course in sensory neurophysiology, and I learned how various things like perceptual illusions could be explained by simple properties of how neurons interact with each other. So here's an example of that. If there's a square that you're looking at on a screen, and the pixels inside of that square have a certain combination of RGB values, okay, you'll see a certain color. You can make them so that they're all equal, about 50%, and then it'll look like a gray square. But if the gray square is completely surrounded by black pixels, it'll look very white. And if it's completely surrounded by white pixels, it'll look very dark. So that you could set this two instances of the same gray square, one inside a black background and one inside a white background, right next to each other, and you would swear that one is way darker than the other. How can this be? Well, it's easy to explain it from the point of view of there are neurons that respond to light, and they tend to inhibit each other if they're near each other. So the ones in the surround that are strongly activated by the white are inhibiting the ones in the square and making them fire less, so it's less bright. It appears less bright. And the ones that are surrounded by black, there's nothing inhibiting them at all, so they'll seem very white. And it turns out that you can see this in the eye of a horseshoe crab. So we have something in common with horseshoe crabs. We have the same lateral nexus of inhibitory interactions that influence the firing of neurons and also presumably the perceptual experience, although I don't know if we would say the crab has experience, but I'm agnostic about that. I don't know, he doesn't, right? But I do know that it helps explain my experience, and I've learned something from studying the horseshoe crab. So I learned something by studying the laws of behavior, and I've learned something by studying the horseshoe crab. But I go to graduate school, and I was interested in the question of what the mechanisms were when people were thinking. And so my advisor also convinced me that I was more interested in humans than I was in pigeons. My research had previously been on pigeons. So I said, okay, you're right. I am more interested in humans. So I started being a human cognitive psychologist because that was the zeitgeist at the time. But I was always a little bit at odds with that. So at that point, human cognitive psychology was essentially based on the idea that the computer is a metaphor of the mind. The mind engages in a series of steps of processing. We first make one decision and then we make another. When we read a word, we read the letters one by one, and then we look up the word in the dictionary after we've recognized all the letters. Things like that. That the study of the physiology of the brain was only of peripheral interest to cognitive psychology because it didn't really matter what the hardware was. It was all about the software that was running on the machine. In cognitive psychology, there was no consideration of brain, and Skinner was anathema because Skinner had ruled out the consideration of the process in between the stimulus and the response. So it was a completely different paradigm.
So you're at this place where you're trying to find the connection between neurons and cognition, right? Between the brain and cognition. And you mentioned that there was this crucial moment, this conference that you went to that really started to open your eyes to how this might be happening. So I'd love to hear a little bit about that.
Right. So when I was a graduate student, this idea that our mind operates by going through a sequence of discrete steps of categorical sort of inference, deciding, is it this or is it that? So when we're recognizing a word, for example, we recognize the individual letters categorically, and then we get the set of letters, and then we go and look it up in the dictionary and see if there's a match, And as a graduate student, I studied the fact that there was evidence that was difficult to explain from that point of view, which was the finding that you see letters better when they're surrounded by other letters to make a word than you do when they're by themselves. So how can that be? And, there were all kinds of important controls that we had to run. And I had started to think about, well, how is it that you could recognize a word better without having already seen the letters and or categorically identified them? So this is a cognitive question I'm asking, right? And the idea I had is very simple. It's just like, well, if the sensory information is a little vague and ambiguous at first, it takes time to kind of develop and become clear. But it's already ruling out certain possible candidate letters early on. Something might look like a block-shaped letter and something else look like a very thin letter. And so those rule out certain alternatives, right? So you'd have a set of candidate letters, and it might be only one possible way to make a word out of all the different candidates in each position. So I came up with some examples of that. Like if you couldn't tell whether something was an R or a P, or some other letter was an E or an F, and some other letter was a D or a B, nevertheless, the only word that would make would be red, right? That's the best word you can make out of those possibilities. And I was thinking this in more or less the verbal ways we're talking to each other about it now. And I wanted to build a explicit kind of quantitative account of this so I could model my data and understand it in more detail. And I went to this conference and I heard a man speak. His name was James Anderson, and he was trained as an engineer, but he had gotten interested in the idea that you could model cognition using neural networks. What was a neural network for him? Well, it was a collection of elements, each of which is like a neuron in the sense that it has a firing rate or a degree of excitation. And the stronger the sensory evidence, the more excitation it would have. Anyway, so this guy gave me the ability to sort of start writing down explicit models in which this was occurring, because we could characterize this continuous activation process using simple equations, and we could explore how it unfolds over time. So these models can be called, abstractly, they're dynamical systems, because they have variables that update themselves over time in response to influences from other variables. Ever since then, I've been sort of using models that contain lots and lots of neuron-like dynamical units that are connected to each other with connections that determine how much they influence each other and whether that's an excitatory or an inhibitory influence. So the connections can be positive or negative, and they can be stronger or weaker. And it's just like, okay, now I know how to do this, or I began to see how I could build models that captured the phenomena I cared about. But it was also a little bit inspired by the brain, and I could build a model that would capture that brightness contrast effect we talked about earlier in the conversation. And so I started to say, okay, these things, maybe we can understand the mind in terms of these processes that happen in the brain and that we share with the horseshoe crab.
And so you ended up writing about PDP, parallel distributed processing, with your partner, David Rumelhart. And then, that really is a seminal work. I'm concerned that, our listeners are probably, not super versed in this idea of neural networks and deep learning. And I wonder if maybe you can summarize to us this process of learning through neural networks with backpropagation. What does it mean? If you can kind of give us a model for the layman who could, to start to understand what's going on there.
Sure. Well, I think the first thing we have to do is kind of have a model of how the process would work if we already had learned. And that was how we started. We said, let us set up the connection weights ourselves, right? So maybe you can imagine this. Set up a little model that could process words that have exactly 4 letters in them. And my collaborator, David, had actually invented his own little font that he could make each of the letters out of a set of little line segments. So a T was a line segment, and another line segment like this, and a capital. There were only capital letters in this font. And then the I was a line segment across the top, a vertical one down the middle, and another one on the bottom. And that was the difference between the I and the T. The difference between the P and the R that we talked about before was there's just this diagonal line segment down there that makes that leg coming off the R, right? Let's say the word is work or something like that, okay? And then each letter then is connected to the unit for the word that it's in. So W in the first position is connected to work, and O in the second position is connected to work, and so on. Okay, so you can imagine if you switch on all these features, then you'll switch on all the letters and you'll switch on the words. So there could be missing information in the input, which would make it hard to know whether, let's say, it was a P or an R, because you couldn't see that part of the input because it was obscured somehow, or it was just left out, or there was noise in the system in some sense. So this is a system that you can, I hope, imagine building out of little things that fire when something is present, and then they connect to something else and cause it to fire when those things are present. So we can build a discrete circuit with switches that come on and off in a discrete binary way when all the relevant conditions are met. And that's, logic gates and logical switching circuits are like that. But in neurons, we think of these processes as more graded and continuous. And so if some of the features or a letter is there, it's partly activated, right? And if all of them are there, it's going to get more strongly driven. If all of the letters of a word are present, it's sort of more strongly activated than if only a subset of them are present, right? And also that these things build up a little bit over time. So a little input comes in and starts activating things, and it starts percolating through the system. And eventually it settles into some state where it's decided that the word is read, even though the letters are ambiguous. So let's now think about recognizing a cat.
Okay.
A cat isn't quite as clear cut as the word CAT in that little font that Rumelhart had made up, right? It's a lot fuzzier, and exactly what features are important. It's really hard to say, right? So, but the idea is that a convolutional neural network is exactly the same as this network I was describing to you before, except that we don't decide in advance what the connections are going to be and what strengths they're going to have. So you start with pixels, a photograph of a cat. Maybe it's, fairly high res image, I don't know. It's a nice rectangular photograph of a cat. And you've got one little neuron-like receptor for each of the possible wavelengths of, so you have RGB in your photograph. So you have three different channels, one for red, one for green, and one for blue at each position in this image. So there's lots of input, and each of these has a graded value in the input, right? It's some intensity of red, some intensity of blue, some intensity of green. Okay, so that's your input. And then what you do is you stack multiple layers of these neuron-like detectors on top, and then at the very top of this stack of multiple layers, you have a neuron-like unit for each of the possible classes, like cat, dog, banana, pelican, giraffe, whatever. So some of these models have 10,000 classes, like different breeds of dogs. So they distinguish, I don't know all that many different breeds of dog myself, but hundreds of breeds of dog even, right? It's essentially the same idea. These things at the output, they're just like the words, and we're just going to, which one is it? What's the best match of the input to this? Now, how do we get the connections that go from these input elements, these sort of different intensities of light, all the way to the classifier level? Where do we get those connection weights from? In a neural network, which uses these graded signals, and where the connection strengths are real numbers, and the values of the degree of activation of each of the detectors is a real number. So you want it to say cat, and it's not saying cat yet, or not strongly enough. So you just look at all the units that are on in that last layer, and you increase the weight from them to the classification, and that'll increase the tendency that this image will cause it to say cat. And if it's saying cat and it shouldn't, you look at the units that are active, and you reduce the connection weights from those units to that output unit. You have to train these networks with massively interleaved presentations of all the different images of cats and dogs and dinosaurs and giraffes and bananas and pelicans and everything else. And it gradually adjusts these connection weights through this iterative process that goes on over extended, repetitions through the entire corpus. And gradually it finds a set of connection weights throughout the entire network that then allow it to produce the correct answer.
In your model that you present in PDP, so you have this really interesting. This is something that and I've been reading a lot about deep learning and neural networks, but I didn't fully, I think, absorb this piece, which is bidirectionality. So this idea that the word can act on the letters. The word, if you think, this could be the word, it can actually help you identify the letters.
Mm-hmm.
What is the significance of bidirectionality? Because I would imagine it must be an ever-present fact inside of neural networks.
Well, so this is a very interesting topic for me. So Rumelhart and I, in the model that I was describing about features and letters and words, we were both very committed to this idea of bidirectionality. We called it the interactive activation model. What that meant to us was that if one neuron excites another, then that other one excites. So that's the interaction. They're talking to each other in both directions. As I was describing the neural network that classifies the image of the cat, we weren't talking about that, were we? We were talking about the activation propagates forward through all these filters until it gets to the last layer. And then the last layer, it's sort of activating the different alternatives. And the one that gets the most activation is chosen. That's an entirely feed-forward process. And that is the standard convention of a convolutional neural network. The error signals propagate, backwards so that you can change the connections at all layers. So there's a bidirectionality, but it's activation in one direction, teaching signals in the other. Rumelhart and I give Rumelhart credit for actually introducing me to the importance of this in general. And I still am very committed to this notion of bidirectionality because it allows us to see how any aspect of our cognition or thought processes or perception, can be influenced by any other aspect. In our model, and in the experiments that Rumelhart actually had done sort of before he and I started to collaborate, what he showed was that if you manipulate how long the last letter in a word is, how long it's on the screen for, that increases your probability of correctly seeing all the other letters in the word. Each letter, the duration of each letter influences how accurately you see each other letter. And that was one way he had of like trying to say, hey, look, it's not just the item itself. It's the context that it occurs in that determines what you see. And this is so fundamental. It's not just who you are, but it's the context that you were born in that determines what you believe, right? So it's all, and we influence each other, though. I'm influencing you, you're influencing me. So it's all an interactive activation sort of system at some level. So this is fundamental to the way we saw things. And Rumelhart wrote this beautiful paper in which he argued that aspects of what you see in a visual input that come together with what you're hearing when somebody speaks influences what word you'll think it is that you're hearing. His example was you were beginning to listen to the word, it might be the word car or the word cat, but you've only heard the beginning of it, the ka, but you already looking at a scene where there's a car and not a cat, right? So you've got this influence saying, oh, maybe there's a car in the scene, and that the word unit for car is active a little bit before the features are all present in the input. And so there's this convergence at the level of the word from the context. And of course, it would go the other way too. Like, what do you see in the image? Well, if the language tells you it's a young woman, you might see the young woman. If the language tells you it's the old lady, you might see the old lady. So the idea that the constraints go from language to what we see and from what we see to language in a bidirectional way, it seems very natural to me. And so I continue to write about these kinds of ideas, that it's all sort of mutually interactive.
You're listening to Remake, a podcast about design, systems, and society. If you're listening on a podcast app, you already know how to follow podcasts. So please follow this one. If you're listening in a browser, just go to remakepod.org to find links to all the major podcast players where you can follow our show.
So if I remember correctly, there were some vision algorithms that could be reversed. So at first it was just identifying things in pictures, and then it could generate, by reversing directionality, it could generate those things. It would say, show me a cat, and it would show some sort of cat.
Yeah.
Is that the same kind of bi-directionality that we're talking about, or is there's like the classification and the creation being potentially two parts of, or two different directions in the same network?
Yes, it's an extremely complicated and rich domain to understand fully how all of that stuff can work out. But it's been a vision that many people have had. And Jeff Hinton, by the way, has also shared this kind of vision. Jeff often thinks about it this way, that the model of perception is really a generative model of the world. And we learn by comparing what we generate to what we actually see and adjusting the parameters of our generative model so it'll match the distribution of what we actually see. Yeah, so one thing I could tell you, a neuroscience experiment that I always found super compelling was one in which the researchers are studying this phenomenon called bistable perception. Okay, so if I'm looking into two separate eyepieces, I can put two completely different images into the two eyes. Okay, I could put a picture of a graduate student in one eye and a sunburst sort of thing in the other eye. It's one example from a classic paper in this. My experience will alternate back and forth between the graduate student in the one eye and the, sunburst in the other eye. So it turns out that, in monkeys, you can get the monkey to report, is he seeing the graduate student or the sunburst? And sometimes you just show the graduate student, so you know that when that's happening, he should always say graduate student. And when you show the sunburst, he should always say sunburst. But then you show them both at the same time, right? And then you find out that the monkey will alternate, and you can also be recording from neurons in the monkey's brain at the same time. And what you find is that neurons throughout the entire visual system, including in the most primary visual areas, are alternating their activation in concert with the monkey's reported perception at all these different levels of the system. So it's like the whole system is settling into a different stable state when it's seeing the graduate student and when it's seeing the sunburst.
Wow.
We have a tendency to perceive our experience as integrated wholes. So, things like if you flash lights while you're listening to music, you'll get this experience that the lights are actually somehow synchronized with the music, even if they're just random. The music sort of, it makes it feel like the lights are doing something sensible because, because you sort of try to establish some coherence between.
I feel like disco clubs could have confirmed that.
Well, they do.
Yeah. So there's something that kind of struck me when I was thinking about this bidirectionality and this sort of recognition that's coming from both sides. And I was wondering if you had the same thought, is this what aha moments are? Because sometimes there's something clicks and you have this feeling of aha. And I'm wondering, is this when these networks just converge and say, okay, this is it. Everything fits.
Yeah. Yes. That's very much the way I think I would think about it. And if you were talking to Jeff Hinton, he would say, yeah, that's right. That's the way it sort of works. When I think about what it means to understand like a mathematical idea, it's like I see how it fits together with something else that I already understood, right? And oh yes, I see that's got to be true because these 2 points are, I'm not going to go into the details of a particular trigonometric relationship or anything like that, but many times we can know that a mathematical equation is valid without it being anything other than just a fact that doesn't have meaning to us. It's just, okay, the sine of alpha plus beta is cos alpha sine beta minus sine alpha cos beta, right? And plus cos alpha sine beta. And it's easy to get the sign backwards unless you actually sort of visualize why it's true and things like that. But when you can construct a visual representation within which each part of those expressions has some meaning in terms of the length of a side of a triangle, the 2 sides of which has to add up to be the length of another side of a triangle, you sort of see why it's true in a way that it all hangs together. So that's how I understand, what a sense of understanding of a mathematical idea is like. And it's very different from, just thinking in terms of formulas as abstract, symbolic rules that don't actually make contact with things like triangles.
Richard Feynman has a whole piece on this. The physicist Richard Feynman talks about. So first of all, he talks about in college he was considered a genius because you could pitch him any theory, any theorem, and he could immediately say is it true or false. And he said all I did was always bring it up to a concrete thing, like furry balls that are of different colors, and then whatever they said in math, I made it real, and then you can have immediately perceive whether it's true or not. And then he I think wrote this whole piece about fragile knowledge, complaining about fragile knowledge when people are taught by rote and in the abstract, and it's not tied down to the concrete reality of physics and of things in the world of water, the refraction of light on the water. He called it fragile knowledge. You can stump people very easily if they didn't connect it.
Yeah, I totally, Feynman is one of my heroes, and I totally agree with those points. It's funny, though, that Feynman isn't the only person who's had to try to fight that battle, right? I have a book written by a professor of mathematics at San Francisco State University on the subject of complex analysis. So complex numbers being numbers with imaginary and real components to them. Complex analysis is sort of like the whole domain of calculus and, relationships in this world of complex as opposed to just real numbers. In the preface to his book, he says that mathematics is usually taught in a way that would be analogous to studying music without ever hearing a note. You're just looking at the symbols and describing relationships among the symbols and not the things that the symbols are actually about, right? So when he thinks about a complex number, it's always a point on the plane, which he then walks you through understanding how to visualize these things on the plane and how to see suddenly very, very complicated formulas that you couldn't possibly imagine could be true sort of are immediately obvious because they're just expressing the relationship between what you can see if you imagine the series of points on the plane and where they would end up after the whole series was completed, for example. So it's the same idea, right? That the truths of mathematics are more deeply conveyed by representing the objects that the expressions refer to and not just the expressions themselves. And to your point about the interactivity or the sort of, things clicking together at the same time, it's like you understand something when you see why it's true from more than one point of view at the same time.
So you call yourself an emergentist. Tell me what that means.
Yeah. Well, an emergentist is somebody who thinks that the characteristics of the entities that we experience including the stars and the galaxies and the, entire universe, even the chemical elements and chemical compounds and their properties and the properties of organisms, right? Like humans and animals and, of course, plants as well, are all consequences of processes that occur at a level below the observed phenomena and give rise to these consequences as outcomes. And it doesn't feel like emergence if I said the total cost of all the groceries in my shopping cart is the sum of the prices of each of the items, right? That doesn't feel like emergence. So that's a case where we understand the total as just being the additive sum of these individual elements. But when things work together in more complex ways, phenomena start to occur that can't be predicted from the elements themselves or some simple process like addition, and only arise in the interactions. The water molecule is one of my favorite examples of this because, it consists of two hydrogen atoms and one oxygen atom, and hydrogen has got, one more proton, one neutron, and one electron, and oxygen's got some 6 electrons in its outer shell and so on. And so, what could be more complicated than that? You add the 2 additional hydrogens and you get a complete shell of 8, and that's why water is a stable molecule, maybe. Okay, so you can understand that, and that's nothing super interesting about that. But what happens is that the protons in the 2 hydrogens are sort of repelling each other a little bit. So they push the angle between them to be not 90 degrees, but something like 110 degrees. And then the water molecule is this thing that has a very complex possibility of interacting with other water molecules and making all of these kinds of patterns that then make water to have a surface tension that is very different from like the surface tension of, I don't know, like ethanol or something like that, right? And so water has all these crazy properties, like it gets bigger when it freezes instead of smaller and things like that, which is not true of most molecules. And it's all about how these things fit together because of this geometry that only exists in the consequence of the outcome of this process. So, what about the human? What about us humans? Well, the amount of sort of things that go on that, together result in us being who we are. They include all these properties of water, obviously, because water is so fundamental to the existence of life. And it's, water holds vast quantities of other things dissolved within it. Life wouldn't exist without water in some sense. But then it goes on from there through all kinds of further processes. And there's another thing about emergence, which is that it's kind of an and not, it's like, it's a consequence of multiple things together and not just a single one, which of course is kind of related to that graded constraint satisfaction idea that we've been talking about throughout. Multiple simultaneous influences give rise to the emergent consequence. In the water molecules, it's all the different ones interacting with each other that makes the interesting patterns of surface tension and crystal structure that are different for water than for so many other things. So in any case, there's this this notion that, well, let's say the human soul, right? Well, where did the human soul come from? Well, an emergentist like me would say that it's a consequence of these kinds of processes that give rise to something coming totally from, this natural process that occurred over evolutionary time that resulted in various predecessors of humans that then evolved further and evolved further and evolved further. And, I don't know which organisms first had something that we would want to think is more like consciousness, more like an experiential element. I have a tendency not to think that the horseshoe crab is fully cognizant as a human being, but I don't know where else to draw the line, exactly where to draw the line. When we think about ourselves and our own sort of like soul or spirit or essential sort of sense of self, maybe that too is an emergent phenomenon.
So I'd like to take us in this direction of technology and AI and, this all this rapid development that I think is striking to people. I'm in a community of, I'm a designer and I'm in a community of designers, and people are really freaking out about DALL-E, which is the new graphic art generator from OpenAI, which can do really incredible things. So you gave this talk about, are we still smarter than machines? So what's your view about the current state of the art and where it's going, and what should we be expecting?
Yeah, I first of all am very enthusiastic about the progress that's been made. I see the work that's been done over the last, back in the 70s and 80s, we had these ideas that I was describing to you. We published the PDP volumes, and they were extremely popular at first. And then there was a lull, and these things aren't really that much, and there's all this. People came back and thinking the hand engineering solutions were going to be the right answer. It was about 10 years ago where that really started swinging back the other way. And Jeff Hinton and his group had a very successful, convolutional neural network of the kind we were talking about before that classified objects sort of suddenly way better than anybody had achieved before. And it really started people moving in this other direction. And so neural networks have been sweeping the field for the last 10 years. And in 2014, 15, I think people thought, we have all the pieces. We're going to see how it all works. It's all going to be fine. And they had these models called LSTM models that were a kind of neural network that had the ability to retain information over an extended period of time. And they were thought to be really strong, language processing models. But then there was another breakthrough, and the other breakthrough was something that's called the transformer architecture. It's at the core of the model I mentioned called BERT, but it's also part of DALL-E. And the transformer architecture came in. Things really changed a lot in 2016, 17, and now everybody's using transformers instead of LSTMs. So I don't think we're probably there yet, right? I don't think that the transformer is going to be the final answer. And I don't think that DALL-E is the final answer, or any of these other really exciting, cool transformer models that people are building these days. I find them extremely interesting. I want to understand them better. My students are working on these things. But I feel like we're going to have another few breakthroughs before we really understand everything. And there are certain ways in which people are still capable of doing things that, these machines are only doing in what I think most people really, if you ask them, would say is sort of kind of, it's like, it kind of gives you the sense that it's kind of like in the right direction, right? It's got these intuitive abilities to construct this cute story or build a picture that's somehow creative and interesting, but they don't have, to me, they don't have a sense of purpose. They have a sense of playfulness and creativity that I think we want to keep. But one of my principal sort of points is that we as human beings tend to be much more strongly goal-directed than our neural networks are in and of themselves. Our contemporary AI systems are in and of themselves. The engineers are directing their goals, right?
Yeah.
So AlphaZero can play Go because its engineers feed it lots and lots of Go games, but it doesn't have the self-direction to decide it wants to learn how to play Go instead of chess or something like that, right? What I'm looking for is a way of envisioning systems that really can be given goals and can then sort of explore those goals and sort of figure out what their sub-goals should be in order to sort of work towards achieving those goals. And can also ultimately, formulate their own goals. What's the boundary between I have a broad goal and I'm formulating sub-goals versus I'm formulating my own goals anyway? And I've found myself thinking, using the analogy of scientists like Einstein or Newton or Darwin or even Rumelhart when he was trying to work out backpropagation, they sort of see there being a question that they don't know the answer to. Newton's sitting there thinking, wait a minute, somehow or other the orbits of the planets and the falling of this apple from the tree are connected to each other. How am I going to understand how that could possibly be? And it took him a long time to work that out, right? It wasn't like the next day he had the answer. And with Darwin, he knew the ideas that people had about how species could have evolved didn't make any sense to him. He couldn't see how they could work. So he spent a long time thinking about that. And, he went around the world on the Beagle drawing pictures of finches and stuff as he was thinking about this. And, finally it started to gel for him. And and then he refined his statement of his basic principle of natural selection. But even after that, it turned out he had nightmares about it. So that contributed to him withholding publication, because I think he was worried about the possibility that he was still wrong. But in any case, this notion of having a goal and thinking, is this going to help me work toward that goal? And that's something I think is currently missing.
Yeah. So I'd love to drill into that a little bit, but I want to ask a hard question. So there's this famous picture now, it's making the rounds of DALL-E 2, where the user asked it to draw a picture of an astronaut raccoon with the universe reflected in his glass helmet and pining for the stars. Right? That was a description. And it created this unbelievable oil painting of this raccoon belongingly looking at the stars. And it's now on Twitter. If a human has created this, it would have good taste. It would have artistic merit. I could, if you want to see it, I could share my screen. I have it here.
Sure.
But so let me share this screen right here. Can you see my screen?
Yeah. There he is.
So say if an artist, a human artist, had made this, I would think that they have looked at raccoons, that they have empathy for, that they can imagine what it feels like to look at the stars, and with longing, that they know what longing looks like and feels like, that they've seen astronauts, right? And I know that this is just a massive data collection of various images, and it's been trained, but this neural network, isn't it just a great artist? I've seen many other great images. Do we start to have to value this network like we value a Da Vinci, and in the sense that it has created this, it has this talent?
Yeah. Well, I don't know if I should be thought of as having a better answer to this question than you do, but I guess I feel like when I think about the talent that was reflected in paintings of Vincent van Gogh or Beethoven always hits me this way too, and Mozart, the theme that ends up being the theme of Beethoven's Fifth Symphony, this thing comes to him, right? Yes, there is a bit of a purpose and goal, but there's also a sense of it coming to him, and it comes to him from the accumulation of his experience, sort of thinking of themes that are going to work to create a sonata form movement. I mean, the guy must have written 1,000 sonata form movements before he sits down to write the first movement of the Fifth Symphony. It's not completely different of a process, and it is something that I consider to be, what makes the creation of evolution, like ourselves, right, so amazing, is that somehow or other our intuitive minds are capable of giving rise to this kind of thing. And Beethoven and Feynman and Einstein and Darwin and Van Gogh, they were all human beings like the rest of us at some level.
Right.
So I think that DALL-E has captured, many of these models are capturing in their own kind of way, something of that character. I don't feel like I can say they aren't. And I think that it reinforces my own view that these things are, in the case of somebody like Beethoven, right, or Van Gogh or other real human artists, they are sort of somehow deep inside the fabric of the intuitive mind that gives rise to this sort of sense of this would be a fantastic way of capturing what I'm seeing right now, as I look out at the starry sky or whatever it is. So I think, yeah, we should be impressed at a certain level, but we should also maybe feel like we're beginning to understand that it actually can arise from sort of massive amounts of experience. So this, it's interesting, right? This comes into conflict a little bit with my insistence on the role of goal-directedness. And I think that it's important to keep a balance between these ways of thinking. But when Archimedes recognized that when his foot went into the water and the water rose, it was going to be the solution to the problem that he'd been thinking about. It was that the problem he'd been thinking about it, he'd been keeping it active because he was trying to solve the problem of, how can I tell what the volume is of this object without destroying it, like melting it or something, And that gave him the answer. But so it's really, again, it's yes and, right? This intuition. Because Beethoven, he did rework his pieces of music extensively. It wasn't like it all came to him, starts with an idea and then he plays with it and gets a version and throws it away and does something else. And so it's a combination of the inspiration and the wrapping it back around through his inspiration and working to make it all fit together and make total sense to him from multiple points of view at the same time, if I could use that expression. So the intuition together with the purposiveness of building something that's really structured and magnificent and also has this theme at its core is, you wouldn't get quite that without, I don't think we're quite there yet with music, for example.
So do you think, do you have any view on consciousness and what, at what point do we call these processes conscious, if at all? Is that a mystical question? Is there an actual test for when something becomes conscious?
So I think of consciousness as definitely being a kind of a non-linear phenomenon, but it's this notion of something clicking when percepts flip from one state to another, like you see that graduate student versus that starburst that we were talking about before. There is a little bit of a transition in between these apparently discrete states, and so there's an underlying continuity that allows for the transition and that has some sort of intermediate elements at the boundary, but then there's ways in which things sort of fall into place and click that are more sort of coherence and discrete aspect like. And certainly, being asleep and being awake has that characteristic as well. And so I think of the sort of awake, alert, sort of conscious state as being a whole complex distribution of states and so on. And I would certainly think of that as different from, let's say, just being sound asleep, or in one of the there's several different stages of sleep, of course, which are also quite distinct from each other. But of course, as I said before, I don't imagine myself that we should restrict consciousness to humans at all. I think of the process of evolution as being one that was extremely gradual, right? So there had to have been, some sort of gradual progression of consciousness-like qualities. And one context in which I think of that is in the context of memory. So, I can have an experience now that reminds me of a previous experience, and I can have the sense of the previous experience somehow coming back to mind. And I think of that, okay, some pattern of activity that was present at a previous time, some sort of pale copy of it has been reconstructed and has some qualities of the pattern that I had when I was experiencing the event itself. And that's my way of thinking about my own experience of memory. I know that animals have the same sort of structures in their brains that we do that are crucial for our ability to learn from an experience in such a way as to have a trace of it that we can bring back later and use just based on that one brief experience. And we also know that if we look at the patterns of activity that occur in human brains when they're imagining things or remembering things, remember what something looks like. It creates activity in the visual parts of the brain. And if you remember what it sounded like, you'd produce activation in the auditory parts of the brain and so on. And I know that animals sort of get activity in parts of the brain that were active during previous experience when they have subsequent experiences that are related to those previous ones. So I have this sense that animals, even rats and monkeys, probably squirrels and all kinds of other animals, are able to reinstate aspects of prior experience in a way that sort of is like having that experience again. And so it's really hard for me to see how that doesn't have some degree of continuity with our own kind of experience. And animals also, of course, they go through different stages of sleep. Some of them have some of the same stages of sleep that we do, or some analogs to that, and others have different ones. But in general, animals, like humans, have different states of activity in their nervous systems, and there's a lot of homologies across species in those regards. So I'm not having much of a reason to think that there aren't sort of consciousness-like aspects of the experience of animals.
And what about the machine? And at what point do we look at a machine and say, oh, it's probably conscious?
Yeah, I think that's an interesting question, too. And I think that my way of approaching it would be to try to develop ways of assessing the quality of that state the same way we do as cognitive psychologists. So we can do experiments that show that people have been influenced by previous experiences that they do not actually remember. And this is particularly easy to do in people who've had brain lesions to those parts of the brain I was describing. So those people will get better with practice doing a task, but they won't remember having done the task before. A neural network is kind of a lot like that. I think of the convolutional neural networks that we were talking about before, or most of these big deep learning-like models, as models that don't really have a sense of their own prior states. They can't really reinstate prior experiences in that same way. They just have this knowledge all in the connections, the same way the amnesic patient does. So the amnesic patient can have an experience of reading a word now, it's having a current experience, even have a faint sense of retrieving a memory from the long distant past, but they don't have any recent past. So it's just a matter of reinstating a state of activation in the system that's distributed enough over enough brain areas to sort of make it somehow coherent. And so that's what I think our consciousness is. It has, of course, it's conditioned on our overall state of awakeness and arousal, and there's brainstem systems that are involved in putting us in the sort of mode where those states are possible as well. So it's kind of a yes and of many things together. But I guess I don't feel like there's any reason to think that we aren't approaching something where we would want to say that there's a sense in which the machine can be aware of its own states. This is not to say, right, that we have access to the reasons why we do what we do. We have experiences that we can report on. But when you ask me, well, why did you become a cognitive scientist? I have to tell a story about myself, right? because I don't have total access to all of the reasons why that occurred either. So I wouldn't want you to think that I would ever think that a machine or a person actually has total self-knowledge as a result of the idea that it had some sense of having an experience. But I do believe that there would be things that would be experienced like about the states of these kinds of machines. And the transformer-like machines have a lot of qualities that are beginning to move in that direction for me. So
nice. So one final question that I usually ask at the end. So in his TED Talk, the philosopher Alain de Botton talks about the difference between a lecture and a sermon. And he says, well, in the modern age, we sort of invented this new modern way of delivering information, which is dry and factual, and then you make up your own mind. It's a lecture. But he kind of longs for the days of people giving sermons, because a sermon is this urgent plea to change someone's life for the better. It's more direct and it seems more caring. So if you had the opportunity to give a short sermon to the world, what would that sermon be?
I guess I would ask people to take on board the fundamental notion that whatever someone else does, or whatever anyone does, myself included and you included and any third party that we would care to admit, including Vladimir Putin or Adolf Hitler, to choose some particularly strong examples, are themselves the product of a confluence of forces of evolution, biology, and experience. And in that vein, we should seek to make the world a better place because we see how it created such aberrations, as opposed to deciding that these aberrations themselves are sort of, the embodiment of some evil agency that exists in some disembodied sense in the universe. I think of Konrad Lorenz as having been the person who first really helped me to appreciate this idea. It wouldn't necessarily be about the Putins and the Hitlers, but it would be about the us versus themness that we have in our world around us. And what Lorenz observed, he wrote a book called On Aggression, which was about things like wars. Having been a German and been through the 2 world wars, that sort of characterized as being a natural consequence of identification with a tribe and the notion that there's the other. So, the whole book is what happens in stickleback fish and what happens in these other species. And it's all about how if the other individual is someone who you see as being part of your same tribe, you will treat them as though they're yourself, and you'll be cooperative and engaged in a positive way with them. And if you kind of distance yourself from that and you put them on the other side of some polarity, you'll see them as being in opposition to you. And then, the hairs on the back of your neck will stand up and you'll engage in an aggressive stance towards them. And so, it's context determines how we react to others, including conspecifics and experience. Evolution creates the tendency to be able to respond in this way because it's important for groups to protect themselves against other groups, right? And evolution made it so that human groups protected themselves against others and would even attack them back if they thought that was in their interests, right? And there's a lot of, you can see justification for that, et cetera. So let's not be judgmental. Let's understand this as a process, and let's all work together to try to figure out how to organize ourselves and our experience and our world around us to feel like we're all part of the same team. And I think that's what Konrad Lorenz was trying to do.
Thank you very much, Jay. I appreciate your time today.
You're very welcome. Thank you, Ira.
Remake is produced by myself and Regina Rothstein. Research and editing by Louis Brady. And audio engineering by Greg Kokoveos. If you enjoyed the podcast, please consider writing a 5-star review in Apple's podcast or wherever you're listening. It helps many more people discover the podcast and also just makes us feel good. Current support for the podcast comes from my own design company, Remake Labs. We're a global strategic design sprint agency aimed at improving outcomes through repeated and rapid design interventions. Now, until next time, be well, everyone, and see you next week on Remake.